Yes. Okay. Cool. So, little disclaimer. This is gonna be recorded. So all of this is going to go to YouTube. For one, well, having this online kind of sucks because, well, it's better to have the whiteboard or whatnot. But the nice thing about this is that, well, this is going to be recorded. So in case you miss something or whatever, it's going to be my YouTube channel. So yeah. So first thing, go to the data science course and go to week 7. And yeah, open that in Colab. Make sure you have that. Send a yay if you have it open. Cool, awesome. See anybody else? Let me see. Put this here. Okay, cool. Okie dokie. So we have 7 people so far. Okay, I guess we should get started then. Okay, so I want you all to tell me how was last class. So last class we did linear regression, right? And we did linear regression and we explored a little bit on gradient descent and whatnot, right? So on a scale from 0 to 10, how confident do you feel about it if you had to do it yourself?
I think for me, I would feel, I'll say 6 to 7, because I understood the concept, but if, let's say, you gave me a new, let's say it's like from scratch, I had to create a project, I'm not confident about that.
Okay. Yeah, because we stopped doing things from scratch. I don't know if you noticed, right? Because now I have like a little template, but before we will code everything, right? Yeah, so that's the thing, right? If we were to code everything, it would take a long time. Yeah. But my suggestion is, yeah, just practice by yourself and try to, let's say that at home, just try to delete all the notebook if you can, and try to do everything yourself. Like, for example, the first part right here, right? It was like, oh, importing libraries. The next part would be, oh, wait, what is this thing doing, right? You can see, oh, wait, this is making blobs, and then you can go into the scikit-learn. You can Google this thing right here, right? And then you can see, okay, that's what it's doing, right? Yeah. So I'm skipping a lot of things, and today we're gonna skip a few things. For example, this one. I'm gonna briefly explain it, but then yeah. Because that's learning this stuff. Some of the stuff I skip it because it's not necessary for the class, right? It's not really something data science is. Those are just tools that are out there, right? But yeah, that's the best thing is just practice. Also, and that's something that the book I made you guys read is not gonna cover because it doesn't cover code. You just cover concepts, right? So yes, the best thing is just that. That's why you work on your project. Say best time to start your project would be after spring break. That because by then you guys will have like at least some of the knowledge of things that you can do, and yeah. So some of these things like linear regression, and today we're gonna cover logistic regression should be enough. Plus, you guys learn pandas and to visualize stuff, whatnot. I send a little tutorial on how to do visualizations. So you guys should be good enough to get started. Not to finish it, but just to get started, We're not going to have classes like the last 2 weeks before finals. So those are classes. We're still going to be there, but we're still, if we actually have the room, if all this coronavirus things it's not there anymore, those are going to be considered our office hours, so you can come by and ask questions. Otherwise, you can, it's going to be a Zoom meeting here, same thing. If school doesn't, schools continue the same way, Anyways, so that's, so that's the thing, yeah. So best thing to do is just practice. Everything is self-contained. You have a question, just let me know. Just email me, be like, hey, I don't understand what this is doing. I'm more than happy to answer those things. So yeah. So let's get started. Cool. So, okie dokie. So, let's see if this works. Let's see. Let me see. Okay, so everybody can see this? Yes. Okay. Cool. So last time we did linear regression, right? So so let's summarize that in like few points. So first thing, we define our model, right? We had our model. In this case, our model was, well, linear, right? We have some data, right? And you're trying to make a prediction of like a line that will predict that data. So one way about thinking about models is that somehow you got some data, right? And that data happens because of something. There's some underground truth behind that, right? The model is trying to approximate that truth. So here, what we did last time is trying to have a function, right, of x, right? And so that's our model, right? The original data is you have x. In this case, let's say that we have, I don't know, let's say miles, and let's say gasoline burn, right? So gasoline, right? And there are some sort of function. So the more miles that you drive, the more gasoline you're gonna burn, right? And let's say they only have available this data, but let's say that later you want to see, okay, what if I travel 100 miles, or what if I drive, I don't know, 1,000 miles, right? You're not gonna drive 1,000 miles in like, unless, I mean, you can, right? But in one day. But let's say you want to ask that question. So this model will like tell you an estimate of how, like, what is the amount of gasoline you're likely to burn, right? So it's trying to estimate the truth based on data. So like thinking about like a model, you can think about it like you're trying to understand a book, right? But to understand that book, you're only given a few pages, and you're trying to reconstruct the whole book just with those few pages. So that's what you're doing with your models, trying to, so you have x, right, which is your independent variable, and y is your output, right? You're trying to find this relationship. What's the relationship there, right? In this case, you don't know. For that, you're trying to get your model, h of x, right? And you're trying to have that model as close to h as possible. Okay. So last time our model was h of x equals to x w plus b, right? So in this case, x was, well, this sort of like, so x could have any amount of features, right? X of x of n, right? And then it's gonna go all the way to, well, xm, x of mn, right? So m, remember, m is the amount of the points, and n is your feature. So how many dimensions that the data has. So what I mean by dimensions again is that, so dimensions is pretty much your amount of features is pretty much you're taking into account miles, right? So for example, say later you wanna predict house prices, right? You're gonna have more things. You're gonna have area. You're gonna have height, right? So that's two dimensions. That's two features, right? And then the more of those two things that it has together, the more pricey the house is gonna be, right? Let's say this is price, right? Oh, let's say this is price, right? And in this case, yeah, so you're trying to predict those things, right? It works the same way. And how do we did that? Our model is linear. So we're trying to calculate these weights, right? W1, W2, W3, blah, 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 Wn. Remember, W is gonna go all the way to n because there's n features, right? So you're doing the dot product with this guy, right? And if you wanna have multiple models, well, this is gonna be, well, model. So all of this were W11. This is going to be W12, W22, W32, right? This is going to be another one, and everything here is going to do a dot product with that guy right there. And then yeah, so that's in case you want to predict multiple things, right? Say that the houses in a certain district have different features than other districts, right? So you might want to do a model per district. That might work too, right? Okay, so yeah, first thing is to find a model. So let's, and the next thing was, well, second thing, we define a cost function, okay? We did a cost, so this would be cost function. right? Okay, so we did a cost function. So if we have our model, say this was our model, right? Okay, so we want to have a cost, like we want to have some sort of penalization, right? If our model's not right, because we want to achieve this, we want to achieve h of x be as close to y as possible. And last time we defined something called j, right? And this was pretty much just this, right? So we just calculated how much the error, the difference between what the model predicts versus the actual truth, and we squared that, right? And then we summed that for every single point in our data set. Okay, so pretty much you're just getting this guy right here, you're just getting all those distances, just squaring them because some of them are going to be negative to make it positive, and then you're adding all of them, and that's going to be your error. So you want to minimize that, right? So this is your error function. This is called actually MSE, mean square error. This is the error function that we have, right? So yeah, so you want to have some sort of penalty to that. And third thing, you want to, well, get your gradients, right? Get your gradients. So you want to find your gradient with respect to your variables of j, right? And the gradient, what's going to tell you is just pretty much the direction of highest increase. So your gradient itself is a vector as well, right? So these things right here, they're vectors, and this would be pretty much the derivative with respect to that, right? So this would be j to, this would be to respect to w1 to respect to w2, right? And usually this is also described as dw, just to make things, you know, dw. I'm gonna be using more dw than this one because I mean drawing a little triangle every single time is gonna take a while, so people call it dw. So yeah, you want to calculate that, right? And lastly, you want to well, update weights, right? So you want to update the weights. I remember the weights are just these values which you're gonna do the dot product, right? One way to think about it, if you read in the book, I think is described chapter 3, is that, for example, if your weight right here is higher than this one, it means that, for example, let's say that this one is area, right? It means that area is more relevant towards the price of your house, right? And if this one's smaller, it means that height doesn't make a big deal. But it might be the other way around, right? So yeah, your weight is like how much importance do you want to give to a certain feature of your data set. That's what the weights are going to be, right? And so you want to update those weights, and the way you do it is as such. Oh no. Let me see. Let me fix this. Oh, let me see. Mouse. Okay, there we go. Cool. I don't like working with the stylus. Okay, there we go. So you want to update the weights, right? So this right here, this symbol means update. So you're going to update them with a learning rate, right? After calculating your gradients. That's it, right? And this was your learning rate. So how big of a step you want to have, because this is a vector, right? So pretty much you have your vector, and dw is just sort of like your, you know, your derivative, right? It's telling you the direction towards you want to move your vector. In this case, by making this smaller or bigger, you're telling it to make it a big step or to make it a small step, right? So this is a hyperparameter, then we're gonna have to tune this. And actually today we're gonna learn a second type of hyperparameter.
Question?
Yes.
So when we update the weights,
yes,
we have this alpha. We're scaling the vector of derivatives by alpha. So that means we're multiplying every entry by alpha.
Exactly.
Is it always the case that we want the same alpha for each W? Like what if for certain, like what if a different learning rate would work differently for each derivative?
So usually rule of thumb is that, well, some rule that is already been done is that for every time step, so W at time t, right? Usually, we're not doing this in this class, but usually people decrease this W. by t. Reason why is because at first in your model, say that you're, I don't know, you're like right here, right? Say that this is like your cost function and you're right here.
Sure.
At the beginning, you want to take big steps, but later you want to take smaller steps, right?
Okay.
Yeah, it's a hyperparameter. So sometimes you might have a really big step, and then you might end up here, and that's not good, right? So that's pretty much your job as a data scientist. You have to figure those things out. And there's no real rule of what is a good hyperparameter. Those are things that you just have to, like play it and check it, like doesn't really, yeah, those are things that you need to figure out yourself by just playing around with numbers. That's all I have to tell you.
Okay.
Yeah. There's a tool that Google's building called Keras, I think it's called Keras Turner. You can Google it. And they're trying to also try to fit this type of value, so you don't have to do it yourself. But it's not it really is not a big deal, because usually I always try 0.01, always try 1. Most of the times it works. And
well, I mean, I guess what I was asking was, you have that learning rate.
Yeah.
We're trying to find n different parameters, right? N different W's.
Yeah.
So, but the way this is set up in step 4, where it says update weights, that's saying is that you're using the same alpha to find W1 and the same alpha for.
Oh yeah, the alpha, you don't change it. Yeah, alpha's gonna stay the same. The only one that you keep changing is DW and W, right?
Okay.
DW.
And I mean, is it ever the case though that it might be more efficient to have like a bigger alpha to find W1 and a smaller alpha to find W2 or something like that?
No. You use treat it as one vector, right? Because the vector itself, I mean, if you do if you do 2 different alphas for each of the vector, think about it this way, right? You have your vector, right? And sure, remember the gradient, it tells you the direction of where you have the highest increase, so you want to decrease it, right? But your vector is made of this, right? And your vector is made of that. If you were to use alpha in those 2 different directions, say that you want to make this bigger and you want to make this smaller, well, when you're doing that, you're changing the direction of your vector, and you don't want to change the direction, do you?
I see. Thank you.
Yeah. Okay. That's why. So by multiplying this to the whole vector, you keep the same direction. You just make it bigger.
I see. Okay. Cool. Thank you very much. That was perfect.
Yeah. Okay. Cool. So yeah, this is a summary of like what pretty much if you have an interview or something, right? This is pretty much how you describe your job. You always have a model. You make a cost function, you calculate the gradients, and update your weights. That's it. That's this class summarized. Hey, have you degree? No, it's not that simple, right? So we're gonna work in each of them right now. So let's get back to it. So let's get to it. So today, let's go with number 1, model, right? So last time we did linear regression. So linear regression, what it does, it gives you a number, okay? So it gives you a number. So for example, we were talking about like gasoline and miles, right? So if I travel n miles, how much gasoline I'm gonna burn, right? So linear regression tells you a number. Take that into account. It just tells you a number, and this number can go from any range, right? So it can also go to infinity, right? Yeah, because it's a linear regression, so it's linear. So it can go from negative infinity to infinity, right? But what it's going to tell you is it's going to predict a number. But there's some applications in which you don't want a number. For example, let's say that given this coronavirus, all these illnesses that are happening out there, right? Let's say that you travel overseas, right? And you say that you have this variable called, I don't know, weeks spent, right? You have some weeks. You spend some n amount of weeks in a certain place, right? And this variable will be deceased. So for example, you have that disease, yes or no, right? So it will be yes or no. Okay. And let's say that here, after, I don't know, 3 weeks, let's put it 4 weeks, 4 weeks or something. We don't know. Like, you have some data, right? You're gonna have people that have here, and then later you have this. Okay. So you want your model to predict this, right? You have some data. You're like, oh, you know what? I want to know exactly how many weeks or how many exactly, right? You want to see 3.1 weeks, 2.1 weeks or so, right? What's the threshold? Where should I, where should I know? In this case, it's easy because you can visualize, right? But then with real data, you have n-dimensional data, and that's going to be hard. That's going to be hard to determine, right? So usually, if you're trying to fit this, right? So in this case, you want to be able to predict 0, like 0 for no and 1 for yes. With linear regression, this is what might end up happening. And this, we did the last time, right? We predicted this, and then we set a threshold. We're like, oh, after 1, you set it up to 1, and everything below 0, you set it up to 0. But we chose that threshold last time. Remember when we did that those little things right here, right? And I was just making you do a dot product to make this thing red, make this thing blue, right? So yeah, we were choosing a threshold to do this stuff. But the problem here is that with higher parameters, you cannot really do this. And then how do we know our threshold is good? Or, how do we know what threshold to choose? So that's not really good, because linear regression predicts a huge amount of numbers. Like, the range is going to be from negative infinity to infinity, while the thing we're trying to predict, it goes from 0 to 1. So this doesn't match, right? So one thing that might work is that we want to predict a function that actually is going to look like this. And what's such function, right? So how people do it is you calculate your linear. So you do your normal linear regression, right? But this is called function z. Z stands for, I'm just going to use notation that's used in this field, right? Z is going to be your linear regression. Okay, this is your regular standard linear regression. But after that, you're going to define your model, and then you're going to pass it to a function. Okay. This function right here, it's called the sigmoid. So let me put it here. So the sigmoid is defined as this. It was 1 plus e to the negative z. Okay, so that's the sigmoid. Okay, let's try to visualize that. Actually, math majors, have you guys seen the sigmoid before? Any of you? Probably not. Probably yeah. Oh, well, okay. So let's
try in biology.
In biology, okay. Mm-hmm. Oh, with concentration rates, right?
Yeah, then and like things that involve like step function stuff too.
And you hit a threshold, right? And then you don't increase that anymore.
Yeah.
Sort of like that. Yeah. So it's similar, right? So let's plug this in. So let's plug 0 here. If you were to plug 0 right here, right? E to the 0, 1, and then 1 plus 1, 2. So 1 over 2, 0.5, right? So at 0, this is gonna be 0.5. Okay. Let's plug in infinity here. Okay. So e to the negative infinity is gonna be 0, because it's gonna be e to the infinity. E to the infinity itself is infinity, but 1 over infinity, it's 0, right? So this is gonna go to 0, then 1 over 1 is gonna be 1. So that means that later you're gonna, towards infinity, you're gonna hit 1. Let's put negative infinity. If we put negative infinity, negative, positive, then this is gonna be e to the infinity. E to the infinity is infinity. 1 plus infinity is also infinity. 1 over infinity, it's 0. That means you're gonna be to 0, right? How this function looks like is like this. You're gonna go like this, like that, and sort of like that. Right? Like it's just a little nicer like this. Okay, this is how this function looks like, right? This is z, right? And this is your function. So the sigmoid function itself is a function that only has the range 0 and 1. So this is powerful because here, now you can make predictions of just 0 and 1. So you can say, oh, very much you're gonna fit your linear function, but after fitting your linear function, you're gonna pass it to this sigmoid. So it's gonna turn all that huge range of numbers, right? Let's say that this is infinity towards infinity. You're just gonna squeeze that into this sort of 0 and 1. So you're pretty much saying, is there or is not there? That's what you're doing. Okay. So so let me see. This is really helpful for multiple things, right? Let's say that we have more data, right? So let's say that we have weeks, but we also have age. Okay. So we might have some people with a certain disease here. And then right here, we might have people with disease 2. Let's say, I don't know, let's say that you have disease 1, disease 2, and then later, and then other type of disease comes up, right? That it's pretty much people have age and have had multiple weeks in that area, right? So how are we gonna do this, right? It's pretty simple, actually. So in your learning rate here, so we're gonna do something called 1 versus all. Okay. So what you want to train here is pretty much say for this disease right here. Okay, let's stick to that one. For that one, you just want to predict those, but then you want to say that, hey, I don't care about these guys. So you're either that one or not that one, right? It's, for example, if I make something that's gonna predict cats, horses, and dogs, right? You're either a cat. If you're not a cat, sure, you're not a cat. You could be a dog or it could be a dog. No, you could be a horse, it could be a dog, right? So you don't care what you don't care, but you're not a cat, you know. So that's the thing. So in this case you're gonna be making 3 models. That's what you're doing, and each model is just gonna be good at doing one thing, predicting one thing. You either are something or you're not. That's what you're doing. So for example, this one, you're gonna do this, and on the other one, well, on this other model, you're just gonna be predicting that, right? And on the third model, you're gonna be predicting just this, right? So at this point, you're just gonna throw a 1 here for this disease, right? And for this one, you're just gonna predict, yeah, you're gonna predict only ones here, and this one you're gonna predict ones here, right? In reality, you're gonna pass your data set to those 3 models. So how you're gonna do that is that, check this out. So this is real. Say this is your ground truth, right? So say that you take this point right here. This one will be 1, 0, 0. Say that you take this point here. That one will be 0, 1, 0. And take this point here. That one will be 0, 0, 1. Okay. This is your y. And then in fact, your data will look like that: 0, 0, 1, blah 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 blah. Right. So this is where you're trying to predict, right? On your model, you're trying to make your model, well, as close to that one, but in reality, it will not be that way. In reality, you're gonna have something like 0.8 here, 0.2 here, 0.3 here, right? And what you're gonna do is, okay, which is the maximum one? Oh, this one, right? Okay, is this a 1 here? Yes, okay, cool, it works. But you're trying to do that, right? So at the end, you're pretty much, your data are gonna pass to those 3 models. And for you to select which category you belong to, is you're just gonna have to look for the maximum value. So which model tells you you're more likely to be. That's pretty much what you're doing. Okay. To achieve that though, what you're gonna be doing, in this case, we only have two features, right? So your X is gonna be X of 1, X of 2, yada, 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 right? And your model on your linear regression, and at least on the Z part, C is gonna be equal to that. It's gonna be, well, W1, W2, right? But in this case, you're gonna have three of them. So this is gonna be W1, W2, W1, W2. But in this case, this is gonna be 1, 1, 2, 2, 3, 3, right? So, and then you're gonna add your bias, right? Your biases are just gonna be like pretty much B1, B2, B3. Okay. And then through that, your model, you're gonna pass it to here, right? So pretty much this features, you're doing a dot product with that one, you're doing a dot product with that one, you're doing a dot product with that one, right? And in this case, well, you're gonna pass that to your sigmoid function, and at the end, you're gonna end up with, well, in this case, you have m data sets, m points in your data, so you're gonna have m. But in this case, it's gonna be, so how many classes? You usually use K for this stuff. So how many classes you want to have? So you have n features and n classes, right? So this is gonna be, your output is gonna be a size m times K, because you're gonna have 3 classes in this case, or K classes. You can have multiple classes, right? And yes, in this case, you're trying to predict either 0, 0, 1 or 1, 1 or whatever, right? That's what you're trying to predict. So do you guys understand this? That's why at the beginning I wanted to touch on this stuff, like having multiple models, having multiple dot products, because essentially that's what you're doing. You're pretty much calculating. You get your data, right? And then you're trying to, in this case, you're trying to have one vector that points this way. You're trying to find another vector that points this way, and then the other vector is gonna point this way, right? And you're gonna do the dot product with those 3, and you're gonna select the one that has the highest value, and that's gonna be your best model for a specific point of data. So yeah, do you guys get this?
I have another question. I'm sorry.
Uh-huh.
I have a question. Didn't you say that the sigmoid was like 1 over 1 plus e to the negative z?
Yeah.
So in this case, though, the if we go back down to that thing you just showed us,
yeah.
Z is going to be that product of those two matrices, right? So is it going to be a M by K matrix, or an M by?
Okay. Yeah. So your Z is already M by K, right? And
Yeah.
you pass H, right? And you pass your sigmoid to that to Z. This is also
right. But how do we make how do we plug an M by K matrix into e to the negative x?
Because that's why Numpy is awesome, because you can just input a matrix, you pass an operation, it's going to do your operation to every single element in the matrix.
Okay, so it's e to the power of everything in the matrix now.
Yeah.
Okay, so we're not changing the input. It's not e to the x with like some sort of matrix input. Okay, thank you.
Yeah. No, this is just a function. You're going to create your own function. And actually, let's do that right now. So that's it. So go to week 7. Make sure you have your thing open. Let's see. Okay, so everybody here? Okay, so first things first. So you're gonna import. If you don't have this open, remember, go to data science course, week 7, click on opening column. So, okay, so again, we're gonna do import numpy as np, import matplotlib dot pyplot as plt, and we're gonna do import tqdm, right? That's tqdm. Remember, that's just for visualization, right? Okie dokie. So make sure you have that. Yeah. So next thing we're gonna okay. So this thing right here, I'm gonna explain real quick what this is. Okay. So here, what this is doing, I'm just creating some blobs. What this means is just I'm just creating fake data, right? And let me show you how this looks like. So this looks like this. So make sure. So in this case, this looks like this. So this is pretty much when I work, because the example I show you, well, it pretty much is the same thing. So yeah. So this data works. This data looks like this. Okay. One thing is that y itself is going to be this value. It's 1, 2, 0, blah 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 blah, right? So, but that's not what we want, because we want it to be, you know, we want it to look like this: 1 0 0 0 1 0 or whatnot, right? So what we're gonna do here is that, oh, first run this piece of code right here, one hot. We're gonna do something called one hot encoding. So one hot encoding, we're gonna do y train equals to one hot y. And let me show you how that looks like. And then we're gonna produce that. You guys have that? Yeah. So the one hot encode is just pretty much just gonna give you this thing right here, and that's what we want to predict, because yeah, this is gonna, because you're gonna predict 0, 1, 2. That's gonna be, you know, you cannot do that. So you have to be able to predict this thing right here. So first of all, our y we turn it into y train. So this is the y train that we want to use to train this model. Now, okay, so let's define our linear function, right? Our linear function, which is what, z equals np dot x of with xw plus b, right? And then we just return z. Or that's just the linear model. That's just z. Okay, so every time we run something, we also want to define, well, we want to create the parameters, right? So in this case, okay, so I added one more thing here. So we have classes and we have features. Okay, so how we're gonna do this is like, we're gonna do np random run n, and the shape that it's gonna take, it's pretty much is gonna be well, features classes. Okay, remember, because your w is this matrix of size n times k, right? And features classes, right? So yeah, we have that. And b is just gonna be np.random. Well, same thing, run n. But in this case, it's just gonna have 1 times classes. And should be able to run that. Make sure you have that. And also to double check that this is working, always double check that your things are working. Just run it here. I'm just gonna do classes equals 3 and features equals 2. See, that works. Oh no, that didn't work. So it says you cannot input a tuple. So let's delete this part right here. Okay, it should look like this. I put an extra parenthesis there. That should, okay, then that works. Yeah, so the nice thing about Colab is that, yeah, if you make a mistake or whatnot, always make a new cell and test your code. You know, because last time I committed a mistake of just keep writing and stuff, and then when we got to the big stuff, right, it didn't work, right? Some of you had errors or whatnot. So make sure every piece of code you run, every piece of code you write, test it right after that it works. So well, you should have something like this, maybe with different numbers, because we're choosing random numbers. So yeah. Okay, so if you got this part to be successful, cool. So if not, remember that week 7 we have the solutions there, so you can go straight to the solutions and copy where you couldn't do it, you know. But that's totally fine. Let's move on. So okay, let's go to here, class logistic regression, right? So within it, we're gonna start some parameters. So here, what we're gonna do is gonna do self params, right? And params is gonna take as an input. Well, the params is just pretty much just gonna take this as start params, right? So when you create your model, you want to start your parameters. But also when you create your model, you want to give it some things, right? You want to give it classes, right? Classes, and you want to give it features. Okay, so you want to pass those things. And also, yeah, let's delete this part right here. Okay, so you want to pass classes and you want to pass the features. So when you create your model, you want to pass those things. You want to tell to your model, hey, you know what? I want to have K amount of classes, but also my data is n-dimensional. So it has n amount of features, right? So yeah, so that's one thing. And also, you also want to create your costs. So sell costs, and that's going to be an empty list, right? Because you want to save all your cost functions, so you just put it there. What else do we need? Oh yeah, so the model, right? So every time we pass the call thing about call is you're just gonna do your model, right? But then your model you're gonna pass your X there, right? And that's gonna be it's pretty much like h of x. Think about it that way, right? So call is just pretty much your predictor. So how we want to do it is that, well, first of all, you want to make your z, right? So in this case, z would be your linear, right? Linear. But in this case, you want to pass some inputs, right? So in this case, you're going to put inputs, and then you're going to put self params w, if you want to do the dot play with that one, and then the next parameter is b, right? So you're just going to do the same thing. Copy paste this guy. We're gonna put b right there. Okay, that's gonna be z. And then, okay, we need to pass a sigmoid. So let's create a sigmoid function. Okay, so I'm gonna do def sigmoid. Okay, sigmoid. Sigmoid is gonna take some value z, right? And what we're gonna do is just this: return 1 over 1 plus mpx. So that means exponential negative z. That's it. Make sure you have that. And then again, double check your code. So sigmoid, let's pass it 0, should give you 0.5. Keep 0.5. Let's pass it a big number. Oh, that should be 1. Let's pass it a small number. I'm just gonna turn this negative. That should be 0. And it's like overflow and counter because it's too big. But yeah, if you pass, would that be? Oh yeah. So yeah, make sure you you have this running. So here, what we're gonna do is just, rather than storing that in here, all I'm gonna do is just return. Oh, return, and I'm just gonna pass the whole thing to a sigmoid. It might look ugly, but it's short, you know. So yeah, so every time you call, it's just gonna apply the sigmoid to your linear function, and that's gonna put your inputs with your parameters of your model, and then yeah, that's just pretty much our model. Okay, so you run this, and you're good to go. Good. So everybody has this. You, cool. Okay. Okie dokie. So we covered the model. So that's the model. Oh. Okay. So that's the model, right? And your model is pretty much just gonna do that. It's just gonna give some predictions, right? What the model at the end is gonna throw is, just remember trying to do this sort of shape, right? Yeah. So let's keep going. So, so the next thing would be your cost function. Your cost function. So one thing that some people might do would be, do the same thing as we did last time, right? you take the mean square error, right? The problem with that, with mean square error, is that once you have your logistic with once you have your sigmoid there, and your cost function, actually, if you go to like plot this JW with MSE, actually looks like this. That means that you, at some point, you're gonna have derivative 0, and you're gonna get stuck there, and that's because you have the sigmoid, and that's a big issue. So in this case, MSE doesn't work. At least doesn't work with logistic regression. So we need a different cost function here. So yeah, so this is called a non-convex function. You want to have a cost function that looks like this. That's convex. Because if it's convex, you're guaranteed to reach a minimum, or you're guaranteed that your function has a minimum, right? A maximum, well, not a local minimum. These are local minimums, right? So you want to have that. And how are we going to achieve that, right? So let me walk through you with this thing right here. So okay, so the cost function for that one, the one we're going to use, don't get scared by this function, but I'm going to walk you through this. So this is called cross entropy. So let me put it here. I'll do log of h of I, and then plus 1 minus minus I, log of 1 minus this. Okie dokie. Okay, so this is our cross entropy loss. You might be like, what the hell, right? Like, this is too much. Let me explain it right now. Okay, so you have two things right here, right? In fact, you only have one, because this one is just the same one as this one, but you only put a minus one minus that one, and then same thing for that one minus the other one. Okay, let me explain why you do that, and let me explain what this means. Okay, so you guys remember from math, how does a log function look like, right? So if a log function has, well, let me put a 1 here. So what should you input to your log to be 1? The same thing, right? Well, okay, no, actually, let me ask the question. What should you input to your log to be 0? 1. Yeah, so your log function looks like this. Right? Looks like that. Right? So your function is 0 when it's 1, right? And it goes through, yeah, so the range of your function would be from 0 to, so the domain of your function is from 0 to infinity, but the range of your function is from negative infinity to infinity. Because when you're approaching 0, this actually goes to negative infinity, right? But when you think it's 1, it's 0, right? But here we're doing a minus. Okay, we're doing a minus. So how this will look like if it's a minus? Well, just the same thing, but just like so I'm just here gonna put a 1 right here. This is gonna be 0. So this is how your function is gonna look like. Okay, 0. So this is pretty much negative log. Okay, and this is infinity. So all I did was just this is your log. This is a negative log. The negative log, by applying negative, I'm just pretty much flipping the function. Okay. Now, if you think about it this way, so what I'm doing here, say that your y, the y you're trying to predict, is 1. Okay. That means, yeah, you want it to be 1. So if it's 1, then your function is gonna be, well, 1 times negative log, which is just gonna be log, negative log, right? And you remember your H is only gonna go from 0 to 1. So if it's 0, whoa, if it's close to 0, you're gonna have a really high value, really high cost. But if it's 1, your cost is gonna be 0. You see that? So if it's 1, log of 1, it's 0. So you minimize your cost. Similarly for the other one. Okay, I'll also, if y is 1, 1 minus 1, 0. So you don't care about this one. You don't care about this one when this one's 1. That's what I'm trying to say. They're both the same thing. So if your thing is 1, you want h to be 1. Because if h is 1, your error is going to be minimized. If h is 0, well, your error is going to go to infinity. Right? Same thing for the other one. The other one actually activates. So if y is to be 0, well, this whole thing is going to turn to 0, right? But 1 minus 0 is 1. So you're going to have the log right here. And in this case, say that h is 1, okay? It's giving you a false positive. 1 minus 1 is 0, so it's going to go to infinity. But if your h is 0 in this one, then it's going to be log of 1. And it's going to minimize your cost, because in this case, y is 0 and h is 0. You want those things to be the same. You see that? So pretty much this one's your cost function for positive samples. This is your cost function for negative samples, right? Because in this case, you're trying to predict the things. You're trying to, in your thing, you want things that are 1. You want them at that point to increase, but things that are 0, you want them to decrease, and this is going to help you to achieve that. Any questions from here? No? Okay. So let's do that in code then. Let's go here and let's go to your loss. All right. So how are we gonna do that? Is that okay? This is kind of huge. So remember, y would be your targets, right? So here what I'm gonna do is just do targets times which is gonna be np log of of model. Actually, you want to do this. You want to define h. H is gonna be, well, h is gonna be just model x, right? So you don't have to define it every single time. So you're gonna do np log of h, right? And then you're gonna do plus 1 minus targets times np log of 1 minus h. Okay. Actually, let me delete this because we don't need this part. Okay, cool. Do you guys have this? Now to this whole thing, all I'm gonna do is just do this. Actually, I'm gonna do this, and I'm gonna divide it. Actually, should I divide it? Yes, I should divide it. I'm just gonna do, well, the whole thing times 1 minus 1 over, no, minus 1 over inputs dot shape 0. Remember, the shape 0 is pretty much just the length. It's just the number m, right? Because your inputs are shape m times n, right? So you want m. M is like how many points you have in your data. So yeah, and then you're gonna return, return error. So that should probably work. Yeah, that should work. Targets, input, yeah, that should be fine. Oh, I fucked up right here. It's model inputs. Because there's no X anywhere, right? Should be model inputs. So your model, you pass your inputs, you get your age, that's your prediction, right? And here, yeah, so here you just do your equation here. So targets times NP log of H, 1 minus targets times NP log of 1 minus H. The whole thing, which is multiply times -1 over M, right? This one right here will be M. If you wanna be more specific about it, well, you want it to look like your actual equation, you can actually do this. It's not gonna change anything, right? Yeah. So times -1 over M. So yeah, so this is our loss function. Okie dokie. So let's run that. So yeah, that should work. So now let's put our fit function, right? Let's create our fit function. So why is this? Oh, what's going on? Huh. I don't know what's going on here. Anyways, so what I'm gonna do here is let me see. Are you guys there? Or did I lose my internet? Oh no. Let me see. So okie dokie. So let's do this. Return self. So what are things that fit should have? You should have your inputs, your targets. Let me check this thing real quick. Oh no, yeah, people are here. Okay, so you have your inputs, you have your targets, right? What else do you have? Oh yeah, your amount of epochs, right? How many times you want to run it? In this case, I usually put 10. And also, what else do you have? I should have learning rate. So I just call it LR, right? Actually, predefined values to be like this. Okay, so this will be your fit function. Okay, so I'm just gonna do for epoch, and well, I'm just gonna do TQDM range epochs, right? All I'm gonna do right here is just do well, I'm just gonna do my cost. I'm just gonna get my cost function. So I'm just gonna do cost equals I'm just gonna do loss. I'm just gonna pass self right here because that's my model. I'm gonna pass my inputs, and I'm gonna pass my targets. And then I'm just gonna do cost dot append cost, and that's it for now. So what I'm gonna do is here is just that every time I run fit, I'm just gonna pretty much put all my cost values there. Okay, so make sure you have this. Make sure you have this. All that this is gonna do is just pretty much gonna create a cost. And yeah, remember that your cost takes your model, takes inputs and targets. All that we're doing here is just storing all your cost functions. So every time you run it, you want to make sure that your cost is decreasing. So you want to keep track of them. That's why you're saving them right here in self.costs. Okay, so cool. Okay, so everybody has this. Okie dokie. So now let's go to the third step. So we had actually, I'm not gonna delete this part, but I should delete this part. I think that works. Let me see. To be honest, I don't know how to use this. Let me just rewrite. So okay, next thing would be gradients. And this might be the one of the toughest parts. So we have to calculate the gradients. So we have that function, right? We have y log of h plus 1 minus y log of 1 minus h, right? And all of that is negative 1m, right? And yeah, like we have this whole thing. I'm not gonna put the sums. You should assume that it's already summing. So we have this whole thing, right? And what we want is to, well, is to have this, right? So a few things that we know is that h is a function of z, and we know that z is this thing right here, right? Okie dokie. So to calculate this, we don't see w's right here, but we see an h right there. So we can take the partial with respect to h, and then we can take the partial of h with respect to z, and then finally we can take the partial of z with respect to w. So I'm just doing chain rule right here. Okay. So let's calculate the first one. The first one is just gonna be, well, with respect to h, right? So what is the derivative of log of h? Just 1 over h, right? So that's just gonna be y over h. How about this one? Derivative of log of 1 minus h. Well, that's just gonna be negative 1 over h. Negative this over, so it's gonna be like minus that 1 minus h. Okay, that's the derivative of that. And then the whole thing, well, remember, it's gonna be negative 1m, right? Let's rewrite this as 1 over m. Let me multiply this one times that one. Actually, so if we do minus minus, it's gonna be plus. Now this one is gonna be the positive one, so it's gonna be 1 minus y, and let's multiply h, so times h, and then minus is gonna be this one times that one, so it's gonna be y minus h, right? And the whole thing is gonna be divided times, well, this one times that one, which is gonna be that. Okay, cool. Now let's calculate the other one. Let's calculate this one. So that one would be, well, just the derivative of this with respect to c. So don't take, okay, so solving that would require a little bit, but take me on this, that the derivative of this is pretty much just this. That's the derivative. Okay, so the derivative of the sigmoid is the sigmoid times 1 minus the sigmoid. That's it. Okay, just if you were to Google that, you're gonna find out. In this case, the sigmoid is h. So all it's gonna be is just sigmoid times 1 minus h, right? And the last one would be derivative of z with respect to w. In this case, that would just be, well, x, right? That's just gonna be x. That's it. So let's multiply them all together, because that's what we want, right? So this one and this one, whoa, you guys see that this one has this one dividing and this one has the multiplying. So yeah, that just turns to that. So what you're gonna have is 1 over m. Let's call this dw. It's just gonna be 1 minus y, h minus this minus h times x. Okay, what else? Whoa, you guys see that this one and this one multiply, so it's gonna be h minus yh minus y plus this one cancel out. Okay, and what we end up seeing right here is h minus y. And you're like, hey, didn't we see this last time? This was the error. Yeah, so it's the same as linear regression. Isn't that neat? After all this derivation. So yeah, so it's just gonna turn to this. In fact, if we're to vectorize that, so this, how this is gonna look like, it just pretty much look like this, right? So you have this I sub 1 to the m, h of I of x minus y of I, and then you have x of I n, right? And remember dw. So in this case, dw, what it's gonna look like is pretty much just like this. 2, 2, 1, 2, 2, and more points. So in this case, this gradient is not really a vector, but it's a matrix. Okay. And how we're gonna do this is because you guys see I, and then I right here. What does that mean? It's a dot product. What is the shape of the dw? Well, the shape of this is nk, right? But you see that, hey, which one? So h has, what's the shape of h and I, or the shape of the error itself? So this error has the shape of ik, right? This one has the shape of in. Okay. So what you see is that we can take the transpose of this. We're gonna turn that into an I, and then the error is just gonna be, well, the error is the same, right? Ik. Now, hey, we can do the dot product right there, right? So how this is gonna look like in code, it's gonna be just this. It's gonna be dw equals np dot x dot t. This case is gonna be the error, right? And yeah, that's it. And also, well, divided by m. And db, well, remember db is the same thing, but it doesn't have x, right? It doesn't have x. So db is just gonna be, well, db was just pretty much this. Just the sum of this thing along m. Because at the end, the shape of this is gonna be 1 times k, right? So it's just gonna be a vector. So yeah, that's why you want, in this case, you wanna keep this, but then the other one you don't care. Okay. So in this case, how db is gonna be, is just gonna be np sum error, and then you're gonna sum along, well, your error. The shape is, well, the shape is m times k, right? So, but you want to sum along this axis right here. So you're going to sum down. That means axis equals 0. And then you're also going to do keep dims equals true. That means that you want to keep the dimensions. Yeah. So all that this is going to be is like, you're just going to be summing along this axis of the error, and that's going to be your db. Okay. Okay. So yeah, taking the gradient takes a while. Like, you have to do the derivation, but once you have it, your code is just pretty much gonna look like this. Very simple. Okay. Also divided by n. Forgot about that one. This is not. What's not working? Oh, okay. Weird. Anyways, let's try this. So your gradient. So your error. What was your error? Your error was just model inputs minus targets, right? Then what was DW? Which is MP. Also, let's define M too. Actually, it's really useful to do that. So I'm just gonna copy paste it from this one. Right. So it's just gonna be MP, MP dot. What was it? Sorry, I forgot. Okay, it's dot T error. So it's gonna be inputs dot T error divided by M. Same thing for the other one. It's gonna be MP sum axis, no, MP sum error axis equals 0, keep dims equals true, divided by M. There we go. You should have this. Got it? Cool. Now, so make sure you run your code. Now, what we're gonna do is like for every single time that you run your epoch, you're gonna do grad. That's gonna be your gradient, right? And no, well, you're gonna do grads, and then well, you're gonna get those gradients. In this case, you got self inputs targets, so you get your gradients. And all you're gonna do here is you're gonna do for key value in
Hey, I'm sorry. Could you return to where we defined the gradient?
Sure. Where? Right here?
Yeah, that's perfect.
Okay.
Okay, sorry about that. Thank you.
That's all good. There you go. So yeah. Okay, so for key value and self params items. So what this is doing is like, because parameters is a dictionary, right? We create a dictionary. So this just goes along the items, and then you have a key, you have a value for every single one of them. Okay. So what here you're gonna do is to self params equals to the same thing. Self params minus, you're gonna do LR, learning rate, and then you're gonna do this thing right here. Oh, sorry, I forgot one thing. You wanna pass your key, because your key in this case will be W, and in a different iteration is gonna be B, right? And same thing for grads. Grads, you're gonna pass your key, but a key, remember we define it as DW and DB. So you're just gonna do D plus key, and that's it. So that should be it. So every time you run, question? Okay. So every time you run this, you're gonna create your cost function, you're gonna append it, and you're gonna create your gradient. You're gonna append it to your cost, then you wanna get your gradients, and for every parameter, you're gonna update your gradient with the same parameter minus learning rate times the gradients. That's it. So everybody should have this. So cool, let's do this. Let's do model equals logistic regression classes. How many classes do we have? It was 3, right? And features equals 2. Let's run that. So if we're to run this piece of code right here, so make sure you have this. Make sure you all have this piece of code. So right here, what it's doing is it gets the model, right? And it's gonna pick the maximum value of the predictions. I'm gonna show you how it works in a minute. And it's gonna plot them, right? And this is what the model thinks. This is the predictions from the model. But the ground truth is this. So it's doing a really bad job, right? So let's fit it. So we're just gonna do model dot fit, and inputs, well, inputs is gonna be X. Targets is gonna be, well, your Y train. And epochs, well, let's run it 1,000 times. Your learning rate's gonna be, I don't know, let's put it 0.1, see what happens. It said, oh, epochs is not defined. Oh, had an error right there. It was epochs. Okay, let's run the whole thing again. Oh, model is not callable. What's not callable? TQDM, man. TQDM. That, I don't know why that happens. Model is not callable. Oh, it was from, okay, sorry about that. It was from TQDM import TQDM. That's in the first line of code. So now that should work. Cost is not defined. Where? Wait, what? Oh, self.cost. Okay, that should work. There we go. Another reason why I coded on live is because so you can see my thought process, but you also can see my mistakes. Because yeah, like it's really easy to make mistakes. So yeah, model.fit. So let's see what it's predicting actually. So hey, it's doing it right. Isn't this better? And if you were to do plt.plot model of costs, you want to plot the costs functions. Oh, what's going on here? Oh, okay. So guess what? The cost functions work wrong. Your loss. Oh, we were supposed to do np sum right here, because your error, this right here is a matrix, but you want to sum every element there. I remember we had that little sum. We didn't do the sum. So yeah, make sure you have that sum right there. So run everything. Model fit. So all you had to do was just add a np sum to the error. So you have, most of you had return error. It was np sum error. So you do that. When you plot your cost, okay, now you can actually plot your cost function. So it looks like this. And then there we go. Now this starts the variable. Now this works. Okay. So cool. So we just built a logistic regression. Actually, how this looks like. Let me do this. Let's do model X, right? Let's see how that looks like. Let's round that. Let's do np round 3. Okay, so this is the output of the model. The model's outputting 0 right here, 0.099 here, 0.24. Wow. So these are the outputs of the model. You guys see this? Right? And the other function, the argmax function, what that one is doing, it's just pretty much doing this. It's just gonna do np argmax, and then you pass model X. What that's gonna do, it's oh yeah, you have to choose the axis too. Axis equals 1. So axis equals 1, it means that it wants to get the ones on this axis, along that axis, and it's gonna choose the index of which one is the maximum one. So for example, this one is the maximum one, right? So 1 is the maximum one. This one is the maximum one, so that's index 2. This one, and this one, which one's the maximum one? This one, right? That's index 0. So yeah, argmax tells you along an axis which is the maximum value, right? And that's what we're plotting here. So we're just giving that little label, and this 2 is yellow, 1 is this one, and 0 is that one. That's what we're doing here. That's why I'm plotting. I'm doing y predict to be argmax of the model along axis 1. Do you guys get this? Yeah. So argmax is just pretty much getting the index of the maximum. Well, number. That's it. But yeah, our model is working great. Okie dokie. So, so any questions about logistic regression? No? Cool, let's continue. Okay, so the next one would be, what if our data was to look like this? It's a circle, right? So in this case, let's say that our ground truth is that, hey, people that are here, you know, are safe, people that are here are not safe, right? Let's just say that. And you have, in this case, you have two types of parameters. So how are we gonna do this, right? Because you think about it, if you think about it, your model, it's only, why is this not working? Yeah, this is not working. Not even working with the mouse. Huh. Yeah, this is not working. Okay, let me close this thing then real quick. Why stop working? What's the name of this? So okay, so your model, what it's doing is just pretty much what your model's pretty much just doing is just doing some selections on, well, it's just separating things on a line, right? It's just doing a decision boundary. And the thing about it is that, sure, that works, right? But the problem with that is that, how are we going to do a decision boundary in a circle, right? That doesn't seem to, you know, oh. Yeah, I guess this thing stopped working. Huh. Wait a minute. Oh, here. Yeah, it stopped working for some reason. Yeah, stop working. Oh well, I'm gonna have to fix this later. Let me see. Well, yes. Actually, I think. Let me.
Hey Luis, I think Zoom has a built-in whiteboard.
I know. I forgot about that. How do we access that? So let me see. Stop working. Oh, annotate. Okay, there we go. Do we? Yes. Okay. Oh no. Okay, what did I do here? How do I stop this? Mouse. Okay, there we go. Yeah. So okay. So let me draw here. Okay. So here our model, what it has is that, you know, you use. Oh, this is actually really good. Okay, so our model is just doing decisions like this, right? Linear, right? So what we're gonna do is add some polynomials to our equation. So what I'm gonna do is, like, so far we had x of 1 times w1 plus x of 2 times w2, right? These are your features, right? What I'm gonna do, I'm gonna add more features. So I'm gonna do plus x1 squared w3 plus x1 times x2 w4 plus x2 squared w5. In this case, the ones that we want is actually this two, right? Can anybody guess why we want this two? Do you remember that in a circle, you might want this to happen? Oh, you might want that to happen. x1, x2, right? A square, that's a circle. Like, that's pretty much all the values from Pythagorean theorem. So you can define this one, x1, x2, right? And your distance is based on the square of both. And all the possible values are going to form a circle, right? Yeah. So in this case, we want those values. Okay. So here's how we can clear our drawings. Okay, there we go. Okay. So how are we going to do this? I have this function right here, called add polynomials. So to x, we're gonna add polynomials to the 7th order. So we're gonna add multiple polynomials. Okay. So how this is gonna look like: x dot p, x dot p dot shape. The shape of that is just gonna be 400 times 35. So in this case, you have a 35-dimensional data. You have 400 points right here, but now I added 35 dimensions. Reason why is because, well, I just added more polynomials, right? So by adding more polynomials, just expect your model to have more to like fit on more dimensions. Okay. So here, what I'm gonna do here is like, okay, so let's create a model. So let's do model 2 equals logistic regression, right? How many classes do we have? We only have 2 classes, right? Well, let's make it 1 class, because one class is enough because we only have 2 things. So you're either one or you're the other, right? So that's good enough. Now features. Features is gonna be, well, xp dot shape 1. Remember, that's gonna be the shape of our thing. That's how many dimensions we have. Okay, so we run this. We see that it's making random decisions, right? Okay. So how? Okay, so let's fit it, right? So model 2 dot fit inputs. Remember, we call it xp, right? And then our targets. What were our targets again? Let's see our targets. Our target is just y. So y. And then epochs is going to be 10,000. And all our learning rate, let's put a learning rate of 1 in this case. Let's run that. That might take forever. Only run it 1,000 times. That's good enough. That's gonna take like 20 seconds. And I'm surprised why it's taking so much. Usually this when I was running this like earlier, this was taking like, I don't know, like 1 second for the whole thing to run. Maybe we're overloading Colab. You know. Anyways, let's see that. Let's double check that our models are running. Model 2 dot costs. Oh no. Let's plot them. I don't want to see the numbers. CLT dot cost. Let's do that. Cool. Okay, so it decreased, right? And we see how our thing is doing. Let's see. Why predict? What's going on here? Wait up. Did I? 1 second. I think I know what's going on. Let me see the shape of this guy. Oh, I see what happened. Okay. Make sure to add this to your code. That should be better. Yeah, so I forgot to reshape this Y. So sorry about that. That should work. And it's kind of tedious dealing with shapes, because remember, shapes are one of the things, and this is why I touched it on that few weeks ago. Shapes are always things that might give you errors on your code. Sometimes your code is really good, it works, but if you don't reshape your data on the proper size, on the proper shapes, then it's not gonna work. Right? So yeah, so that, oh, okay, yeah, so let's see how it's doing now. What's going on here? Huh. Okay, that's weird. Reshape X with P. Huh. Funny. Let me run this again. Last try. I'm surprised. So model 2, let's just run it 100 times. Okay. Okay. Oh, and that worked. Oh, check this out. So you guys see this? It actually predicted something right. You see this? So okay. So let's look at it closely, because we only predicted based on those points, right? And that might be a good thing, that might be a bad thing. Let me explain you why. So I'm gonna run the next piece of code here. Check this out. So this is the decision boundary. So pretty much I made a grid that's gonna be all the possible points within this range, and I predicted what's gonna be based on our model, right? Here it did it right, but here it predicted some extra things, right? And we were not able to visualize it. So what's going on here is that our model. So sometimes you might have data, but your model, if you have too many polynomials, might end up overfitting your data. And what's problematic with this is that, say that you have a data set here, a point right there, and you're trying to ask a question to your model, it's gonna be totally wrong. Reason why is because it's too well fit to the data. And that's a really big problem, because we don't want our model to be that fit to our data, right? In this case, we've seen that it overfitted, and it's throwing weird things. So if you were to ask, okay, how is my model doing at this point? It should be blue, but he's like, oh, it's doing red, right? Because it fitted too much of the data. Like the polynomials were like, oh, you know what? I'm gonna fit to W, I'm gonna fit X1, I'm gonna fit all these values, have a bunch of features, might as well fit them, right? So this is not good. So what we're gonna do here, it's just gonna, okay, so how do we take care of this into account, right? How are we gonna do this? So one of the things that we're gonna do is that we're gonna redefine our cost function. So I'm just gonna say J total. It's gonna be our J cost plus J rec. This is gonna be our regularization, okay? So how this one looks like, J cost is the same. This is the same one as we did. But J rec, what that one is gonna look like, it's just gonna be lambda over 2 times W squared. And then we're gonna sum, well, we're just gonna sum all of it. Yeah, so we're just gonna sum all the W's, okay? Why are we doing this, right? So we're gonna keep a penalty. Remember, your J is a penalty, right? J is a cost function, it's a penalty. We're gonna keep a penalty if your W's are too large, okay? How do we calculate the grading of this? Well, so in this case, the grading of this, right, of frac, it's just pretty much just gonna be the derivative, which is just gonna be J lambda W. That's it, because the derivative of this is 2 divided by 2 cancels out, same thing, right? So and your total dW is gonna be like this. It's gonna be W. dW is gonna be your normal dW from your cost plus this guy right here. And then how you're gonna update W is gonna be your normal thing, W minus lambda minus lambda over M dW plus lambda W. Okay, so lambda is just another hyperparameter. This is called the regularization factor. So you have learning rate, and then you have this one. Now you have two parameters to be tuning. Remember, so the W is pretty much, it's just giving a penalty to your W. So what's going to happen every time you apply gradient descent, you're going to be decreasing W. It's just you want to be decreasing your weights. You want to decrease some of your weights, but there's going to be a point in which you're going to be decreasing your weight, but it's going to affect this cost function, right? It's going to affect your model, and then later, this one's not going to matter anymore because your weights are already too small, and if you make them smaller, this is going to get bigger. So this is like, hell no, you know what? Actually, I don't want to decrease that much, So you expect that most of your weights are going to go down. The ones that don't matter are going to go down, So for example, if you have your thing right here, right? If you apply regularization, then you're going to have some weights, but it's not going to go as bad as before because this model is good enough too, right? So what's going to happen? Is that this right here. So the higher the lambda, the more regularization you have. So that means the smaller your weights are going to get. So usually a value of 1 is good enough to decrease your weight. If you do 100, that might kill your model. It's going to pretty much turn all your weights to 0 straight on. Sometimes you want to have a small regularization factor. So then again, these are hyperparameters, So these are parameters that you have to be tuning yourself. Just give me 5 more minutes and we're gonna be done. Okie dokie. So this one didn't clear. Okay, so how do we add that, right? This is just gonna be some small piece in our code. So here to logistic regression, all that we're gonna do here is that we're gonna add rec, which is gonna be the regularization, right? In this case, I'm just gonna put 0.1. And then to our gradients, we're also we're also gonna pass rec. We're also gonna pass rec, okay? And then to our gradient, we're also gonna pass rec. And on DW, what's gonna happen here? I'm just gonna add plus model params W. This is gonna be rec times that. That's it. And then parentheses over the whole thing. Run this. So I'm just updating DW. DW is just gonna have that regularization. And then here, I just have rec right here, and it's just gonna be included in your gradient. So you don't need to change much things here. And then that's it. So if we are to create our model again for this thing right here, so let's run this, model that, this, and then we pass rec equals 0.1. Actually, let's run it for 1,000 times. See how that works. Okay, cool. Okay. It's still predicting good. And oh, we see more things, right? That means that, hey, we might need a stronger regularization. So in this case, I'm just gonna put a 1. See how that goes. Let's try this one. Okay, it decreased. So if we pass more, like say 10, let's see how that's gonna do. We make sure it's decreasing. Okay, slow enough. Let's run this one. Boom, disappeared. There we go. So now we don't have those artifacts. And now we're able to see, hey, we passed multiple amounts of parameters, but now our model is selecting the ones that are good. So this is good because sometimes this gives you, the main takeaway from this is that here regularization allows us to, 1, not overfit our model. That's a good thing because we don't want to have a model that's not reproducible. And 2, you can have a huge amount of polynomial values, right? And regularization allows us to pick the right ones without us implicit, because in the right one in this case is x1 squared plus x2 squared times the weight of each of them, right? But sometimes we cannot know that. Sometimes we cannot visualize the data in 2D, right? So sometimes you might want to have a data set, and this is what I was going to make you do later. But we're going to cover that next class actually. But actually, let me show you on the solutions. So here's the solutions. So what I was going to show you is that we have data sets. For example, let's say that we have numbers, right? 5, 0, 4, 1. This is like handwritten digits, right? We're going to turn these guys into vectors. But the thing is that we don't know what features to choose from those things, right? But regularization is going to help us do it. So in this case, we fit our model. It has 0.70. All I did was just do the same thing. Model 3. I just passed my training data. All I did was just to fit it. I just fit it. That's it. Same way as we did it with these things right here. And then if we were to visualize how these vectors look like, they look like numbers: 0, 1, 2, 3, 4, 5, 6, or whatnot. And this is this data set is like a 700. Well, actually, how many dimensions does it have? It has 700 times. Yeah, 700 dimensional. So it's 28 times 28. I don't know how big that number is, but it's huge. It's big dimensional. But we see that this logistic regression that we built, it's able to fit it. So it's really powerful. So this tool that we built works with n-dimensional data. Works with data sets that you can do it with images. You can do it with, for example, you can use logistic regression, say like for this new data sets. Actually, the coronavirus data sets are becoming really popular right now, and they have all this sort of like parameters. Yeah, you can set up you can set up all those parameters as one dimension. You know, then it works as long as you specify how many classes, how many features, and how many times you want to run it. All you do is create your model, fit it, boom. There you go. So yeah, any questions? Nope. Okay. Well, so see you guys next week. Next week, the things we're gonna learn is that wasn't it tedious to do the derivatives?
A little, yeah.
Yeah. So we're gonna learn a tool that's gonna do the derivatives for us. So you don't have to. You're gonna have to skip. You're gonna be able to skip that stuff. Yeah. So yeah. So I guess today is the last day we're doing derivatives. But hopefully you guys understood it. You know, it's just those four points. Create your model, your cost function, get your derivatives, update your values. Simple. That's all it is. Okay, cool. So so now would be read chapter 4. Chapter 4 is actually my favorite chapter in the book. It talks about the history of how these models came out. I don't think they touch the history of logistic regression, but they touch on how they started to think about it back in the day. Like you get to see the thought process of how they call it learning rules, right? So it's an interesting chapter. So that's chapter 4. Chapter 5 is more technical, but yeah. Yeah. Any questions? Just let me know. You know. Yeah. Be safe. Wash your hands.
Yeah, be safe, everyone.
All right. You guys.
Bye.